Hello and welcome. This is a heat exchanger problem. It's the condenser of a power plant where steam, hot steam, is being cooled by cooling water. So we'll say steam comes at state 1, goes out at state 2. Cooling water comes at state 3 and goes out at state 4. And pressure, temperature, and information are supplied about each of these states. And we are asked to find the flow rate of mass flow rate of the cooling water, and along with some other things such as the rate of heat removal from the steam, how much heat is being lost by the steam to the cooling water. Notice that the entire system, overall system, is adiabatic. There is no heat transfer to the ambient atmosphere. This is an example problem, so the manual solution is already there, so I don't have to really go over it, but just to show you where you can find it. The manual solution is accessible. You can just examples, and all the examples are isolated. You go down and it's one of the last problems. Yep. If you go unrestricted solution, manual solution, right there is the solution. So as you can see from the given information, all the enthalpies are calculated, entropies are calculated at the ports, and then the energy equation is put it together. And the entropy equation you can use to find the entropy generation, and the energy equation will give you the mass flow rate. Essentially, the energy equation reduces to heat lost by steam is heat gained by water. Leaving the details aside, let's go and launch the correct app. First of all, the app for this would be obviously it's a system analysis, so we will follow system analysis, open system, open steady system, generic, and finally it's a non-mixing multi-flow system. So we click there, and PC model obviously because steam and waters are involved. Steam and water are involved, so we go launch the app, and in the I/O panel we isolate all the variables that is given to us, which I have done in this tab. This is just to save time. I have launched different copies of this app. Okay, so in the I/O panel, I'm organizing everything that is known, given value. State 1 and 2 are my inlet and exit state of steam, and state 3 and 4 are exit state of inlet and exit states of the water. And the information given I have just documented here. Mass flow rate is given in kg per hour, note that, and pressure is given, the delta, the rise in temperature is given as 10 degrees Celsius at the exit. So this is a parameter, we can later on say, what if the answer, it's not 10 degree but 12 degree. We can just simply change it and do a super calculate. Okay, so with that, the calculation of internal heat transfer we'll do later on, just bear with me. So we'll go to the next here. So again, here are the value that we know. In the state panel, we can copy the information, P1 kPa, and wait a minute, in the I/O panel, the information known, we must hit the calculate button first. Now P1 kPa will be understood. Similarly, we can, X is given to us, and again, I have finished the work to save time. So for state 1, as you can see, pressure is given, quality is given in fraction, and mass flow rate is given in kg per hour. So therefore, state 1 is found. That's the steam inlet. For state 2, similarly, pressure is same because there is no pressure loss. Quality is given, and quality is saturated vapor, so it's 1, and m dot 2 equals m dot 1. One way to make sure that you picked up the correct value is to take a look at this ribbon, at this output panel. This is a help panel at the top. If you put the pointer over the fraction, x2 is 0. It's saturated liquid. Steam enters as a saturated mixture, goes out as a saturated liquid, and the mass fraction of vapor is 0 to specify sat liquid, which is also shown here, saturated liquid. State 3 is the inlet state of liquid water. Again, pressure is known, temperature is known, and we don't know the mass flow rate, so we leave it unknown. But for state 4, pressure, temperature are known, and m dot 4 I'm writing equals m dot 3 using the mass equation, because the liquid water coming in must be, the mass flow rate must be equal at the inlet and exit. But see, the white background means we don't know m dot 3 yet. We just leave it there like this. Okay, we now go to the device panel, and a non-mixing device is by default the choice here. So let's set up, say, steam goes in at state 1 and it comes out at state 2. Water goes in at state 3 and comes out at state 4. There is no heat transfer, there is no external work transfer. You got to make sure you don't make a mistake there. State 1 goes out at state 2, that's the steam. Liquid water goes to that pipe 3 to 4. Let's do a calculate. If you're correct, you are going to go back to the state panel and you will find that mass flow rate has been calculated and pasted for you automatically. If you do a super calculate, of course, it is going to produce all the results along with the test codes. All the test codes are here. And the answers that we are looking for in this problem, calculation of internal heat transfer. Oh, by the way, to find that, we go and set up device 2, which is just for the steam, single flow going from state 1 to state 2, and there is no external work transfer. If I calculate, it calculates how much heat has been transferred out of the steam. Negative means steam is losing heat. So in the I/O panel, the Q loss would be negative of that Q dot 2 by 1000. If I do a calculate, that will produce my answers. So Q dot loss from the steam is 14.83 megawatt, and entropy generation rate is of course picked up from device panel 1. S dot gen 1 is same as the entropy generation of the system's universe. So this is the answer to part A, and this is answer to part B. And for what if scenario, you can always go and change any of the input given variables. And if you look at that, if we change these variables that are given, any of them, and just click the calculate button followed by the super calculate button, any plausible what if scenario can be calculated, explored.